Okay, so today, let's just work on number one, okay? I'm just gonna do this off my head, so I have the solutions, we'll look at it after, but let's tackle this, okay? So you have this velocity versus time graph. How many sections are there on this graph? Okay, so we got 1, 2, 3 sections. So let me just do it over here. So section 1. So we got to find that equation of that line, right? So we know y equals mx plus b. And I'm going to call this v1 equals m t1 plus b. The slope is delta v over delta t, 20 minus 0, 5 minus 0. What's that, 4? And then the y-intercept, 0. So v1 is 4t1, correct? I would hope so. Yep. Cool. I'm just going to find the velocities in each section, and then we'll go through the calculus, okay? Second one should be real easy, right? Section 2. V2 is just 20. Okay, section 3. We can still use the same formula, right? Y equals mx plus b. Yep. Tell me that again. Yep. Oh, yeah. So this is just finding this. This is really the slope. Oh, yeah. Yeah, I got you. 60 minus 20. Yeah, I'm just going to do it this way. Yeah. What's the time? 30 minus 20. So what's that? 40 over 10. So 4 again? Yep. Yeah, and then we'll just plug in. So let's plug in 60 and 30. And what's that? 120 negative 60? Same thing. Yep. Cool. Right. So we now have the velocities for each section. Now we want to find the accelerations. So what's A1 equal? What's the fundamental equation for dynamics? dv1 dt? So acceleration in section 1? It's the 4, yep. And if you look, the rate at which we're increasing is just the slope of a line, okay? Cool. Where did the other half go? There you go. All right, A2 is 0 because the velocity is constant. And then A3 is also 4. Yep. So getting the equations and doing the derivatives are the easy part of this problem. The hard part is the integration and finding the right constants, okay? So V1 equals dx1 dt, or was it S? Let's use, yeah, S is for rectilinear motion, 1 degree, yep. So what you need to do is, I'm going to put it over here, because you have to integrate. You got to put your limits in correct. So this starts at 0 and goes to S1. This is T01 of 0 to T1. So we have to plug in for T1. So this is just S1 minus 0, 4T1 squared over 2 from 0 to T1. 2T1 squared. Is that what you got? Yep. It does do that. Yep. All right, I'm going to do the second one, and then I'll have you try the third one. Okay. So this is still the same fundamental equation. What are our limits on the left? It's, yeah, so it's the initial value for S, or it's really the final value of S1. This? So S not 2 is SF1. This, yes. It's, why did I put F? I'll put S1F, the final value. Okay. And then this is T not 2, which is what? Was it 5 seconds? Yeah, 5 seconds. And then we put just T2 up there. You remember why we leave the top as variables? Because that's how you integrate, and you can actually find the equation. If you just plug a number in there, you're actually finding a number. You're not finding the equation. Okay, so remember that. So I'm going to put it down here. I may erase this line. What's the final value? It'd be 2 times T1, which is 5 squared, ds2. And I think this was 20, right? From 5 to T2. So this is S2 minus 25 times 2, 50, equals 20 T2 from T2 to 5. So S2 is 50 plus 20T minus 20 times 5, correct? $20T minus 50? That's 100, yeah. So you could do the same thing for case 3, right? You just have to put your limits in right. Now, You notice what we're doing here? We're doing the same thing as the shear moment diagram. Think of the shear as V, which is V in shear moment diagrams. If you integrate that, you get the moment equation. When you integrate that, you get position. Okay? So it's the same style, same exact stuff. You're just looking at dynamics now instead of shear moment diagram forces. Okay? Want me to do the last one? And then we can check when you plot it to see if it works. I always like to write the fundamental equation. We're going to integrate ds3, integrate v3, d2, dt3. This is S0 which is S2F to S3. What was the time? 20 seconds? The initial? Okay. T3. And what was our equation here? 4T3 minus 60. 4T3 minus 60. Uh, 20, right? Four T3 squared over 2 minus 60 T3, T3, 20. So this one gets a little trickier, right? Am I losing anybody? Kind of just chugging along. Yep.
Yeah, you haven't lost them both. You just wait where you're going on these drops. Those are your position.
This.
Oh, so you just check your.
I took this equation and plugged in 20 seconds. Yep. Correct. Yep. Yeah, a lot of 20s in here right now. Yep. Yeah, I was kind of chugging through this. Sorry. What's that? It only integrates this. So you have to figure out what this constant is when you do sims. Yep. Yep. There is a way that you should be able to do it. I think you have to make sure to plug these in. And then you have to add this somehow. Yep. So what's this? Hold on. What's this? Is that 400 minus 50? So 350. And then this is 2T3 squared minus 60T3. All subtract 2 times 20 squared minus 60 times 20. Now, I don't know that number. Yeah, 800 minus 1200, or minus 14, minus 400. So really plus. So S3 minus 350, 2T3 squared minus 60T3 plus 400. We should check this once we plot it. Minus 60T3 plus 750. Can you plug in 20 seconds here? Let's make sure we get 350, right? This should be 350. Is that right? $350. Cool. That's a good check, right? Because this initial point should line up to this final point.
How did you get the 350 to check to make sure it's right?
Sorry, say that again, Michael.
How'd you get the 350 to check to make sure it's right? Did we get that earlier? I just missed it.
Yeah. All I
Oh,
did
oops.
was I took this equation
Right.
and I plugged in 20 seconds, which
Oh.
is the start of section 3, and I knew the final of section 2 is 350 from this.
Oh, okay.
Okay.
I didn't realize where we got that 350 from section 2.
Yep.
Okay, thanks.